For those of you familiar with the notion of order and number theory, we're looking for an integer that's not equal to 1 such that so it's an integer elevated to itself, or the base and the integer, the same thing, is congruent to 1, modulo 31. Okay. Now, what this means is that if you divided 31 into a raised to the a, you would get a remainder of 1. So we're looking for something in this form. Now let's move along and just briefly talk about how the order is defined. The order of an integer a, notice that it's not equal to 1 because 1 raised to any power is just 1, so that's not interesting. So we're looking for an integer a other than 1. Now, the order of an integer modulo b, a modulo b, is the smallest integer k such that a to the k is congruent to 1 mod b. Now, a simple example of this would be 4 is the order of 2 modulo 5, because 2 to the 4th leaves a remainder of 1 when you divide it by 5. 2 to the 4th is 16. 16 divided by 5 is 3 times 5 plus 1. So it leaves a remainder of 1. And again, this is mod 5. Now, I won't write it all down. This is mod 5. But notice it's the smallest. It's the smallest such integer. Well, 4 is certainly the smallest integer because 2 cubed would be 8, which would relieve a remainder of 3. And then 2 squared is just 4, and that's 4 mod 4. So 4 is the smallest integer that enjoys this property. Okay? So let's move along and look at another fact that I'm not going to prove. The order of an integer mod a is always going to be a divisor of this Euler phi function. Now, y'all, this Euler phi function just counts the number of elements less than of the input argument that are relatively prime. Now, prime numbers have a wonderful property. In fact, you could define prime numbers this way. 31 is a prime number, and it has 30 it's equal to 30 because all 30 of the numbers less than 31 are relatively prime to 31, or it wouldn't be a prime. Okay. Now, in general, phi of just as a side, phi of p, and again, you could almost define the phi function first and then define prime numbers next if you wanted to. I think maybe there's something wrong with that, but phi of p is always equal to p minus 1, and that simply follows immediately from the definition of a prime number. And again, the phi function is a counting function that counts the number of integers less than the input argument that are relatively prime to the input argument. Okay. Now, so this is equal to 30. This fact that I didn't prove, it's something that's proven in a number theory textbook, has the divisors 1, 2, 3, 5, 6, 10, 15, and 30. So you see that it follows that we're just going to check these type of numbers, right? You see, what are we trying to do here? We're trying to find out we're trying to find out the order. And so the result probably I should write down also is that a raised to the phi of p, let's see, phi of p, okay, is congruent to 1. My opinion. That's assuming a and p are relatively prime. But this is something I probably should have written down earlier. Okay? So this is a fact, and so that's why this is useful. Okay? Now, let's move along and just take a look at the possibilities. Okay? So 2 squared is equal to 4. Okay? Modulo 31. We're doing modulo 31. I'm not going to write it down each time. That's not congruent to 1. 3 cubed is 27. Again, that's just 27. It's not congruent to 1. Now 4 cubed, a little bit of work here. What did we get? We got 8. Y'all right here, notice that 4 cubed is congruent to 2. And again, just in the name of brevity, I won't. If you take 64 and divide it by 31, you get 2 times 31 plus 2, right? 2 times 31 plus 2 is 64. And so what you can replace 4 cubed with 2. 2 times 4 is 8. That's not congruent to 1. Okay? Now, let's see here. For 5, I split 5 to the 5th as 5 cubed and 5 squared because And y'all notice this, in my opinion, this is easier than just writing down whatever 5 to the 5th is and dividing by 31. You can do it in a kind of a creative way to minimize your computations. But notice that 125 is congruent to 1 mod 31. Why? Because 125 is equal to 4 times 31 plus 1, right? 4 times 31 is 124, right? So you see this 1 that you see here is the same as this 1 right here. So you see how this object is just equal to 1 modulo 31, and you never had to go to the trouble to even know what 5 to the 5th was. That's kind of neat. That's the power of modular arithmetic, all right? So anyway, you get 25 here, which is not congruent to 1. Now also, we can kind of work, we know for a fact what's going on with, well, actually we don't, do we? 6 squared? Yeah, 6 squared right here. Y'all, the reason I did this is kind of, you're using this fact and this fact simultaneously, but 6 squared is congruent to 5. Right? Because 6 squared is 36, and when you divide 36 by 31, you get a remainder of 5. But we already know what's going on with this. We have 5 cubed, and we already know that that's 125, but we already know that from over here. So you see how as you move along when you're doing this stuff, sometimes previous steps help you in your calculations, and we never even had to know what 6 to the 6th was. It's a huge number, right? But we're using this modular arithmetic in a very nice way. And so what we've learned right here is that 6 to the 6th is congruent to 1. And it's in the form. Remember, it's in the form we're looking for. And so that is our answer. 6 to the 6 is our answer because it's in the form a raised to the a power. Okay. So again, a nice problem, I thought, just to use some facts. Some of these facts, this is non-trivial to prove. This is just a definition here. This requires some work to prove that the order of an integer is a divisor of phi of the integer, or phi of the modulo. Okay, phi of the modulus. It's a divisor of phi of the modulus. So, and I chose a prime number just for grins. We could have used numbers other than prime numbers here, but it's just easy. You can quickly write down what phi of any prime number is. So I used it. 30 turns out to have these 8 divisors. Okay. And so I didn't check any of the others. 10 may work, 15 may work, 30 may work, I don't know. But I know that 6 worked. Okay, so we get, we found one example. Let's see here. That would be 6 raised to the 6th. It's congruent to 1. Mod 31. Again, just think about how you would have done this if you just tried to calculate 6 to the 6th and divide by 31. There's multiple ways to do modular arithmetic. I think I picked the path of least resistance. But anyway, so the answer to the question is 6, of course.